non-defective media in the palladium instant SRI. If you can fill up all the octahedral sites, then when you inject extra deuterons, you have a chance of some of those who go 2 per site to make local molecular states. And that seems to be very important for the SRI experiments, which appear only to work with bulk poisons up in the mid-90s, 0.95 fractional occupation. Other questions?
What about the tetrahedral sites at the higher, at the levels of deuterium concentration at which you get maximum effects? Tetrahedral.
You get some occupation in tetrahedral sites. The problem is that you got a saddle point between the octahedral and the tetrahedral site. And the saddle point sort of argues against trying to get them to tunnel together. It's much better if they're in a molecular state in bed in the same site. Because you can calculate, I've actually calculated in detail overlap probabilities for different site occupation, same site occupation. There's maybe 30 orders of magnitude difference for same site occupation.
The other question related to the phonon models, have you, if you include anharmonicity in the vibronic, would that be a substitute for going to many sites?
The way I view that, there's 2 important effects. One is that your oscillator, because of that harmonicity, isn't an oscillator, harmonic oscillator anymore. And I've actually calculated this physics in the presence of non-harmonic oscillator. The answers are essentially the same. You don't get much difference at all. The other issue is that if you have anharmonicity, then you can begin thinking about driving an acoustical phonon mode very strongly. That couples to an optical phonon mode that has some fractional occupation. Optical phonon mode. The optical phonon mode can bring the deuterons close together, which is what you need to establish a matrix on. So anharmonicity extends the frequency range over which you can have the possibility of having an interaction. So in that sense, it's very important.
Yeah, because actually, again, experimentally, anharmonic, hydrogenic, and deuterium modes have been identified.
Right, of course.
At those frequencies.
The local deuteron frequencies is measured by neutron, slow neutron scattering. Shows a very anharmonic local potential.
Here, you're presupposing 2 deuterons close to one another. How many of these things do you need? How close do you have to be?
Actually, the calculations are starting to give those numbers.
You say many sites. What's that mean?
Well, here, I mean, I can actually start reading off here. I've done calculations where I've had like 2 or 3 sites now with compact states of helium talking to a single phonon mode, and I get Jones type effect things. Turns out I need something like 12 or 15 deuteron pairs interacting with a single phonon. Well, your phonon, optical phonon mode, if it's lossy, is probably in the order of 1,000 angstroms or less. Keep the strength when I got the number on there.
The last question.
If there's gain that can be bigger, if it's acoustical, it could be a little bit larger. If the loss is less, it could be a little bit larger. But if you got like a dozen inside the 1,000 cubic angstrom region, then this physics should turn on. But that's common. In the modeling of the nuclear interaction, including phonon exchange, I get an analytic form.
You're saying the lattice is causing this?
No, on a microscopic scale, you've got the 2 deuterons, which are, in the absence of phonon excitation, they tunnel together. In the picture of them tunneling together, they're kind of like sitting next to one another with this quantum mechanical spreading, tunneling going on.
Within 10 Fermi or something?
Well, you can have, theory says you can have 0 overlap, aside from probably, forbidden exclusion principle. But there's no reason. I mean, the overlap probability of 10 fermion and 0 fermion, within 20% of one another, or something for 2 deuterons. So the picture is that you somehow managed to tunnel somewhere together. Now, the lattice is very highly excited, and the 2 deuterons can be thought of as part of the lattice. lattice phonon is very highly excited. What that means is your two deuterons are going to have a small response that's consistent with your lattice excitation. And you can use local linear response theory to calculate the response of your two deuterons locally at short range to include the effect that the phonon mode has on them. And that's where the phonon exchange probability comes from. Because that motion now, a relative motion, a very tiny varying scale, an incremental motion that these things have being driven by the lattice that contains angular momentum. In fact, the amount of angular momentum contained in the motion, the amount of potentially available angular momentum is actually zillions of units. However, if you calculate things out according to the exchange model that I've worked out, you actually need something like a couple of Fermi's motion before you can exchange 10 phonons. So, we're starting now to get numbers of correspond to response, the actual microscopic distance that the phonon motion has to cause these things to move in order to exchange enough phonon quantum to generate nothing.
So we have a chicken and egg problem here.
I don't know if it's a chicken and egg problem.
These things are able to excite phonons.
But what it means is that if you either got acoustical phonons, which aren't effective exchanging phonon nuclear interaction, or you got optical phonon excitation that's not too strong amplitude, then the amount of motion locally is very small, which means that you can only exchange a couple of phonons, period. And if you exchange only a couple of phonons, then your initial molecular state is helium-4. Helium-4 projects into unstable compact states. So these things live for 10⁻20 seconds.
So how do we get the state?
You have to get your phonon mode wound up. An
How do you
optical.
get your stable? How do you get your phonons? You get stable.
If you were in a lab and you had a terahertz source, you might shine the terahertz source on the surface and generate it. If you were in McCouvery's experiments and many other people's experiments, if you drive the flux of deuterium inside the lattice down a chemical potential that's 50 millivolts or more, the flux of deuterium down a chemical potential, sudden discontinuity, is the most efficient way of generating optical phonons that I can think of. There is no method more effective for generating optical phonons than that. In the current generation experiments, the Eilenberg experiment, the recent Newton experiment, all of McCouvery's experiments, Miley's experiments, all now have a recognizable deuterium flux component